we have studied, we started from graph theory, then we studied mesh method, node method, Telegon's theorem, right. All of that we studied. Then we studied phasors, right. How do we deal with sinusoidal steady state circuits? And after that we developed a battery of network theorems, right. What all theorems did we do? We did Telegon's theorem, of course, then reciprocity theorem, then superposition theorem, Norton and Thevenin's theorems, and maximum power transfer, right. And then we did source transformations also. You have probably done in the tutorial source transformations. So, source transformations, converting Thevenin model into Norton model, vice versa, right. So, all of this we have done, and right now we are in a state to move forward. Okay. What we are going to study now are two port networks, and basically you already know what is a two port network. Do you know? We have done it before. You know what is a port, right. During reciprocity theorem we actually did two port networks, right. We did a two port network while studying reciprocity theorem. So, the two port network is basically some network with two pairs of wires sticking out. So, in this module what we are going to study is the theory of two port networks. So, we are going to do much more than what we had already done. So, I have two ports P 1 and P 2. You are always going to put P 1 on the left side, P 2 on the right side. I mean, generally speaking, that is what is done. The network is something which has all LTI circuit components, right, R, L, C, M. It can also have controlled sources, voltage controlled and current controlled voltage or current sources, or both, right. But the network does not contain any independent source. So, I am writing LTI on top to indicate that it has all linear circuit components like whatever I have mentioned, but I am also writing no independent sources. Okay, and it is critical, it is vital that this network not have any independent sources inside, right. None of this theory will apply if we throw in independent sources into the network. Okay, all of whatever, this entire module will collapse. Fine. So, the network does not contain anything independent. So, no voltage source, no current source, but dependent sources are allowed. Okay. Now, this P 1 and P 2 they have a voltage and they have a current. So, you are going to we are going to look at the voltage V 1 at port 1, the voltage V 2 at port 2, and the convention for current is that it always has to go into the network at the plus terminal. Okay, this is a fixed convention. I1 and I2, they have to go into the network at the plus terminal. All right, this is a convention. Okay. So, this is the basic 2 port network. Fine, this is what we are studying. 2 port network, no independent sources, LTI components are there inside, and then V1 at port 1, I1 going into the plus terminal at port 1, V2 at port 2, I2 is going into the plus terminal at port 2. Fine, this is the basic setup. All right. Now, if there are no independent sources, then generally speaking, what do you know about V1, V2, I1, I2? What are these values? They have to be 0. Why? There is no permanent energy source, there is no independent source, right. And if there is no independent source, nothing is going to happen, nothing at all is going to happen. V1, V2, I1, I2, they are all going to be nicely, happily equal to 0. Okay. So, as long as this black box, this 2 port network, as long as it is there in the shop, where it is there on the shelf somewhere on the shop, right, not connected to anything, it's all the voltages, all the currents inside are going to be 0. Now, you purchase it, hook it up with other things, other batteries, other voltage current sources, it is going to start doing something, right. But till then, till that point, it is all at 0. Fine. Now, the way we can use this is as follows. We can apply a voltage source V 1 at port 1. We could also apply a voltage source V 2 at port 2, right. So, for example, can we think of this? Let us apply a voltage source V 1 at port 1 and let us apply another voltage source V 2 at port 2. Okay. Now, before you apply V 2 at port 2, can we use superposition? Superposition theorem is valid or not valid in this case? Valid, because there are no other sources involved. Okay. So, for example, I 1 will be equal to something times V 1 plus something else times V 2. Is this okay? Because of superposition, right. First you make V 1 equal to 0 and apply V 2, then you make V 2 equal to 0, apply V 1, right. The net result, when you have both V 1 and V 2, it is going to be the sum of the two. This is okay. So, I have used superposition to say this, and similarly I 2 is also going to be something times V 1 plus something times V 2. Okay. You can call these, give these variables, these are all variables, alpha 1, alpha 2, alpha 3, alpha 4, whatever you want to call them, right. We will have other names for these things in future, do not write alpha 1, I am just indicating that they are not the same, right. They are all different constants. What units will they have? What are the units of these constants? Siemens. All right. So, units are Siemens, right, different constants are there, agreed. Okay. So, this is one possibility. Another possibility would be that let us not put V 1 and V 2, let us have a current source at port 2 and a current source at port 1. right. We could do this also. There are many ways to play with this 2 port network, right. I could play with it by applying 2 current sources at the 2 ports. I could play with it by applying 2 voltage sources at the 2 ports. And then what else could I do? One current, one voltage, and one voltage, one current, all these possibilities exist. Okay? So, there are many ways to play with this 2 port network. So, for example, if I apply I 1 and I 2, then V 1 is going to be something times I 1 plus something else times I 2, and V 2 is going to be something times I 1 plus something else times I 2. Fine. Is this okay? And if I apply V 1 and I 2, right, then those two become the independent variables and V 2 and I 1 become the dependent variables. Right now, in this case, I 1 and I 2 are the independent variables, because those are the two sources. V 1 and V 2 are the dependent variables, because those are what you measure, right. That is the response of the circuit. Okay. So, you can choose. So, how many variables are there, by the way? There is I 1, it is a variable, I 1, V 1, I 2, V 2. There are 4 different variables, out of which it would be okay to choose any 2 as dependent variables, any 2 as independent variables. So, how many possibilities are there? 4C2, 6. Okay, so, there are 6 different ways to play with a 2 port network. Fine, 6 different ways to play. All right. So, we are going to cover all 6, right. Each of these ways to play with a 2 port network, right, we are going to discuss in detail. Fine. So, for now, let us consider I 1 and I 2 as the independent variables, what is on the screen, right. I 1 and I 2 are the independent variables, and V 1 and V 2 are going to be measured. All right. So, by now you have learnt that whenever there are a pair of 2 equations, I am not going to write 2 separate equations, I am going to put them in the form of a matrix. Okay. So, I am going to write as follows. I am going to write V 1 and V 2 are equal to some matrix times I 1 and I 2. And what is the size of this matrix? 2 cross 2. What are the units of the different things in the matrix? Ohms. All right, all of these quantities are in ohms. So, we call this the Z matrix. Okay. So, we are going to call it Z11, Z12, Z21 and Z22, to be explicit over here, right. This is this parameter set. So, these are called the Z parameters or the impedance parameters. Or you can call it the Z matrix, impedance matrix, whatever you want to do it, right. There are many different ways to talk about it. All right. So, if somebody says we are talking about the Z parameters, what are we talking about? Yeah, we are talking about this matrix. Okay. We are only talking about that matrix. That matrix is called, that 2 by 2 matrix is called the impedance matrix or the Z matrix, Z parameters. Fine. Is this okay? Good. Because if you have done so far, then you would also be able to say that Z 11 is nothing but V 1 by I 1 when I 2 is equal to 0, right. Remember superposition experiment. What did we do in the superposition experiment? We said let us make this source 0, right. Let us apply I 1 and measure V 1 V 2, right. That measurement tells you Z 11, okay. And it also tells you that Z 21 is equal to V 2 by I 1 when I 2 is equal to 0. Fine. I 2 equal to 0 is also, what does it mean? I 2 equal to 0? Port 2 is open circuited. Port 2 is just open. All right. So, let us call this open circuit 2, port 2. Fine. So, I open circuit port 2 and I measure V 1 by I 1, that is going to give me Z 11. I will measure V 2 by I 1, that is going to give me Z 21. In other words, I open circuit port 2, take a 1 ampere current source and push I 1, push 1 ampere into port 1. Then V 1 will give me Z 11, V 2 will give me Z 21. Fine. All right. Likewise, what is Z 12 going to be equal to? V 1 by I 2 when I 1 is equal to 0, and what is Z 22 going to be equal to? V 2 by I 2 when I 1 is equal to 0, and again once again we are going to combine this, right. It is a single experiment that we will do with two measurements. Okay, we are going to do one experiment. What is the experiment? Open circuit port 1 and push 1 ampere into port 2, measure V 1 that will give me Z 12 and measure V 2 that will give me Z 22. Okay. This is the plan. Let us do an example. Now, I hope you have understood by now that the examples that we do in the classroom, they are always going to be easy ones. Ones in the tutorial are slightly harder, and the ones we are only going to do easy ones. However, we always do illustrative nice examples in the classroom. The ones that we choose both in the classroom as well as in the tutorials, they are always going to be nice. There is something important to learn and take away from these examples. So, we are going to start with this. Of course, this is my port 1 and this is port 2. Okay. And this particular network, the shape of it is like a capital T. Okay. So, it is called a T network. Fine. Some people also call it a Y network, because you can tilt Z1 and Z3 a little bit and it will look like a Y. Okay. Some people also call it a star, although it does not really look like a star, it looks like the the star with only 3 spokes. Okay. But nevertheless, many people, lot of people call it a star. You also call it a star. You have called it a star before. Huh? Yeah. When you did some delta star at your coaching, wherever you went, right? Right, they called it a star. So, this network, it's really, to me it looks like a T, but nevertheless, right, many people call it different things. Star, Y, T, all kinds of names. Okay. So, let us do this. What is our plan? We want to find, what do we want to do? We want to find the Z matrix, the Z parameters for this 2 port network. All right, that is the objective, to find the Z parameters for this 2 port network. And then in future you can use the 2 port network under different conditions, right, that is for future. For now we are going to figure out what are the Z parameters. So, what do we do? What are the experiments we are going to do? First experiment, open circuit port 2 and push I1 into the port 1, push 1 ampere into port 1. So, I open circuit port 2. So, this is open circuit left hanging, and over here I push 1 ampere into the circuit. Okay. And then you have to make 2 measurements. One measurement is V1, the other measurement is V2. What is V1 going to be? What is Z3 doing, by the way? Can there be any current in Z3? No, no current in Z3. Okay. So, Z3 is just hanging around. So, what should be V1? 1 ampere into Z1 plus Z2. So, Z11 is nothing but Z1 plus Z2, that is Z11. Fine. Okay. Then we also have to measure V2 in the same experiment. What is V2 going to be? I have pushed 1 ampere into port 1, port 2 is open circuit. What is V2? It is going to be the same voltage as this. These two voltages will be the same, because there is no current in Z3. So, the drop across Z3 has to be 0, no current in Z3 means drop across Z3 is nothing. Okay. So, 1 ampere into Z2 is the voltage across V2. Fine. We are doing these 2 experiments. This pair of measurements, we did one experiment with a pair of measurements. Done. Now, we do the second experiment with the second pair of measurements, these two. Okay, this is my plan. We'll do this. How do we do this? We have to open circuit port 1 and apply 1 ampere, push 1 ampere into port 2. So, let us now open circuit port 1. So, we open circuit this and we are going to push 1 ampere over here. Fine. Let us push 1 ampere into the network. What is going to be V1 and what is going to be V2? So, first let us find out V1. Z2 times 1 ampere, and what is going to be V2? Z2 plus Z3 times 1 ampere. Fine. So, this is the impedance parameter set, right. This is the Z matrix for this particular network. This is the Z matrix. Do you have any questions? Yeah, good, good question. That these two are equal, the matrix is symmetric. Will it always be symmetric? What do you think? If there are dependent sources, it is not going to be symmetric. Okay. Recall reciprocity theorem. What was reciprocity theorem? Do you remember reciprocity theorem? We have it here somewhere. We had statement 1 of reciprocity, statement 2 of reciprocity. Do you remember? This was reciprocity theorem. So, statement 2, I pushed a current I1 into port 1 and measured V2 at port 2. Isn't that what you did just now? That is the experiment to do to find out Z21. You push I1 into port 1 and measure V2 while port 2 is open circuit. When you are using a voltmeter, port 2 is open circuit. Okay. So, that would have given you Z21. So, this gives you Z21. Okay. And in D, what did you do? You pushed I1 into port 2 and with a voltmeter you measured the voltage across port 1, and this was the same experiment as Z12. Okay. And reciprocity theorem tells you that these two are equal, which automatically means that Z12 and Z21 have to be equal. Okay. But reciprocity theorem is valid under certain conditions. What condition is it valid? All right. Any questions so far? So, if the circuit has, if your network has active components like controlled sources, then it is the matrix is not going to come out to be symmetric. But otherwise, if you have passive components, then symmetry is guaranteed. If you are not getting it to be symmetric, then you are doing it wrong. So, that is a sanity check, right. At the exam you can use these as sanity checks, right. You see that, oh, my Z 12 is not coming equal to Z 21, must be doing something wrong. Fine. All right. So, this is one way of playing with the two port network. Remember, we have to cover 6 different ways. This was one way. The second way is that let us, instead of applying current sources at port 1, port 2, let us apply voltage sources at port 1, port 2, which basically means that V 1 and V 2 are the independent sources. So, I 1 and I 2 are going to be measured. This is going to be some matrix times V 1 and V 2, which are the independent variables. All right. What are the dimensions of this matrix? Siemens. All of the parameters are going to be conductances, admittances. So, this is called the admittance matrix. Just like the earlier one was called the impedance matrix, this is called the admittance matrix, admittance parameters, or we call it the Y parameters. Okay. And to be explicit, inside the matrix you have got y 1 1, y 1 2, y 2 1 and y 2 2. Okay. So, I 1 is equal to y 1 1 V 1 plus y 1 2 V 2, and I 2 is equal to y 2 1 V 1 plus y 2 2 V 2. Fine. This is the plan. What can you say about y 1 1? What is it equal to? Y 1 1 times V 1 is going to be I 1. So, y 1 1 is going to be I 1 by V 1 when V 2 is equal to 0. Fine. And y 2 1 I 2 by V 1 when V 2 is equal to 0. V 2 is equal to 0 means what? Port 2 is a short circuit. So, both of these measurements. So, I am going to apply a 1 volt voltage source when port 2 is a short circuit. Fine. I will apply 1 volt, measure I 1, measure I 2. I 1 measurement will give me y 1 1, I 2 measurement will give me y 2 1. Okay. We are always going to proceed column by column, not row by row. Okay. Every time column by column, be careful. Fine. Next experiment, we are going to look at y 1 2, which is nothing but I 1 by V 2 when V 1 is equal to 0, and y 2 2 is nothing but I 2 by V 2 when V 1 is equal to 0, which V 1 equal to 0 means port 1 is a short circuit. Fine. All right, let us do an example, and this time okay. So, this particular network, just like the previous one looked like a T, it was called a T network. This one looks like the Greek capital pi. If you ignore this wire over here, then it looks like the capital pi in Greek. Okay. So, it is called the pi network. Right. Some people also like drawing it like this. Right. Now, it looks like a pizza pie, right, a triangle, not a triangle, that the pizza pie, it looks like a pie from the pizza. So, that is why it is called a pi network. Okay, then you will have to add an E over here. It is okay, right. You can add, you cannot add, it is fine, right, pi network. Some people also call this the delta network, right, because the earlier one they called star, this one they called delta, right. The reason why is because this looks like an upside down Greek delta. Okay. All right. So, we are going to find the y parameters of this 2 port network, and to find the y parameters we have to do 2 experiments. What are the 2 experiments? The first experiment is we are going to short circuit port 2 and apply V 1 at port 1 and measure I 1 and I 2. So, let us short circuit port 2 and we have applied V 1 over here, fine, not V 1, let us apply 1 volt over there. Let us apply 1 volt at port 1, and then what is I 1 going to be? What is, first of all, what is Z C doing? Will ZC have any current? No. The potential across ZC is 0, it can't have any current. Okay. Now, I have applied V1, all of this V1 is going to drop across ZA and ZB, and therefore, what is I1 going to be equal to? Okay. So, 1 by ZA times 1 by ZA plus 1 by ZB times V1, fine. So, my Y matrix is Y11 is nothing but 1 by ZA plus 1 by ZB. This is I1. Okay, and then I2, be careful because you are looking at the current going backwards. Minus 1 by ZB times V1 is, or V1 is 1 volt. So, minus 1 by ZB. Fine. Great, because now we are ready to do the second experiment, and in the second experiment we are going to apply V2 and short circuit port 1. Fine, and measure I1, I2. What is going to happen now? ZA is not doing anything, right? ZA is short circuited out. So, the input resistance is nothing but ZB in parallel with ZC, right. In other words, Y22 is going to be 1 by ZB plus 1 by ZC, and Y12, that is the measurement of V1, sorry, the measurement of I1, and remember I1 is going backwards into the circuit, right. You have applied V2, right. I1 is going to be minus 1 by ZB times V2. Fine. So, effectively this is what it is. Alright, this is what the entire scheme of things is, right. Earlier also we did this, yeah, earlier also this is, right. Okay, let us do it. Okay. So, first of all, oh, by the way, you need to tell me one more thing. If I1 I2 is y times V1 V2 and V1 V2 is z times I1 I2, then what is the relationship between capital Y and capital Z? What is the relationship between the Z matrix and the Y matrix? Y has to be equal to Z inverse. They are inverses of each other. All right, or Z is Y inverse, either way. Okay, and suppose I tell you that we chose a different circuit when we wanted to do the Y parameters, but if I asked you what are the Y parameters of this particular network, of this T network, right, you could have simply inverted the Z matrix and told me what are the Y parameters. What are they? Can you invert and tell me? So, first of all, what is the determinant? Z1 Z2 plus Z2 Z3 plus Z3 Z1, because Z2 squared cancels out. Okay. So, the inverse of this, yeah, fill in the blanks please. Okay. This we did just by inverting. You need not have done this inversion. You could have simply gone ahead and done the two experiments that we had discussed for computing y parameters. That would also give you the same result, exactly the same result. Okay. So, the y matrix corresponding to this T network is this. So, this is the y matrix. Fine. Okay. And what if I asked you to do the find the Z matrix corresponding to this pi network? I do not think I want to find the inverse of this matrix. Okay. It looks horrible unless you go to the y domain, right. You could, for example, write 1 by z a plus 1 by z b as y a plus y b, and this is minus y b, and this is minus y b, and this is y b plus y c. If you write it this way, then finding the inverse is very easy. However, let us just do it once more just for practice. You know, we are also beginners. So, let us do it once more for practice. Let us find the z parameters for this two port network. We just like we found the y parameters, let us find the z parameters. Okay. I mean, no harm in doing more practice. You already know how to invert a 2 by 2 matrix, right. So, what do I want? I want to find the z parameters of the same circuit, and the way we are going to find the z parameters is by using my two experiments, performing my two experiments, right. Open circuit port 2, push 1 ampere into port 1. So, I open circuit port 2, this is open, nothing on port 2, right. Push 1 ampere into port 1, push 1 ampere into port 1 and measure the voltage V 1, measure the voltage V 2. Is that okay? Open circuit port 2, what happens? ZB and ZC are now in series with each other, right, and together they are in parallel with ZA. So, the potential V 1 is going to be ZA in parallel with ZB plus ZC. Fine. Is it okay? All right. Now, I want to measure V 2. How do I do it? 1 ampere, it goes, the 1 ampere goes and hits this node over here, and now it is going to divide up. On one side it sees Z A, on the other side it sees Z B plus Z C. So, it chooses how much of it goes through Z B plus Z C, Z A divided by Z B plus Z C times that 1 ampere goes through that part. Right. And then what is the drop across Z C? Z C times that current. Fine. All right, experiment 1 is done. Now, go ahead with experiment 2. Experiment 2 was push 1 ampere into port 2 while port 1 is open. And it looks exactly the same as before, right. And in this case Z C is going to be in parallel with Z A plus Z B, right. And therefore, okay, that is going to be V 2. And V 1, that is Z 1 2, we can use Rahul's observation, reciprocity theorem, and simply declare this as Z A Z C by Z A plus Z B plus Z C. Fine. So, this is the Z matrix corresponding to this network. You could have also arrived at this by doing the inverse of the Y matrix, but we just did this to get a little bit of practice, right, tiny little bit of practice. Okay. Now, going back to the star delta conversion, right, much feared star delta conversion is coming up, and our statement is that if I purchase two networks, network 1 and network 2, okay, I purchase two 2-port networks. I do not know what is inside the networks. Okay. Contents inside are not revealed to me. I have purchased these two. I take them back to the lab and do my 2-port parameter measurements, and lo and behold, I find that the 2-port parameters are exactly equal. All right. Then my claim is that these two networks are equivalent to each other. They are not identical to each other. I do not know what is inside, but they are equivalent to each other. I can substitute one network with another as long as the 2-port parameters are the same. Are we agreed on this? Fine. Now, I open up and see, oh, one was in a star formation and the other was in a delta formation, right. This one was like a T, and N2 was like a pi. All right. their 2 port parameters are the same, and therefore, I can replace one with the other with no effect on the outside. Right from outside I do not know which is which, but when I open it I see one is star, the other is delta, then they are equivalent to each other. Are we clear on this point? So, in that case what do I do? If what does that mean? That means that this Z matrix, the Z matrix of the T network and the Z matrix of the Y network are going to be equal to each other, right. And similarly, the Y matrix of the Y network and the Y matrix of the Z network T network, they are also going to be equal to each other. Fine. If the Z is equal to the Z, then the Y is also going to be equal to the Y, because Z and Y are inverses of each other. All right. So, let us do a comparison. Let us do a comparison with the Z. This is the Z. This is the Z of the pi network, and the Z of the T network I will cut and paste over there, so that we can do a comparison. Okay. So, this is what I had. Okay. Now, you do parameter by parameter comparison. What do you see? First, what do you see? Z2 has to be equal to what? ZA ZC by ZA plus ZB plus ZC, right. Immediately you see it, and you also see that therefore, if Z2 is known, then what happens to Z1? ZA ZC is taken, right. So, Z1 has therefore, has to be ZA ZB by ZA plus ZB plus ZC, and therefore, Z3 has to be equal to ZB ZC by ZA plus ZB plus ZC, right. Z2 is equal to okay. So, if you know the pi or the delta network, right, if you know the delta network, if you know ZA, ZB, ZC, now you can work out what is Z2 and therefore, what is Z1 and what is Z3. Fine, I am writing only 1. This is the reason I am writing only 1, because so this one we are going to rearrange it a little bit and we are going to draw it as a triangle. All right, and the pi sorry the t was simply this Z1, Z2, Z3, which I am going to rearrange, and which was Z2. Yeah. Okay. So, the way to remember is Z2 is in between ZA and ZC. So, Z2 shows up over here. All right, and because Z2 is in between A and C, so it's ZA ZC by ZA plus ZB plus ZC. Fine, this is how you remember it. All right, now what if the star is known, but you want to find out what is the delta? And now what do you have to do? You have to compare the, last time we compared the Z parameters, now we are going to compare the Y matrix, Y parameters. Okay. So, the Y parameters over here, right, the comparison is a little ugly if you, right, this is the Y parameters. So, shall I cut and paste? Okay. So, what do you see over here? You see immediately that YB, this one by ZB, I am looking at this, right. This particular one has to be 1 by ZB has to be equal to Z2 by Z1 Z2 plus Z2 Z3 plus Z3 Z1, right, or in other words YB has to be equal to so much, or in other words you could say ZB has to be Z1 Z2 plus Z2 Z3 plus Z3 Z1 divided by Z2. Fine. Now, how do you remember this? How do you remember which transformation, which formula to pick? This is the big question, right. First of all, you have to realize that both the formulae are the same. They are the same formulae. If you look at, right, let's instead of looking at ZB, if I look at YB, what is YB equal to? It is equal to Z1 Z2 plus right. But let us multiply numerator denominator by y1, y2, y3 just for fun. Okay, I am going to multiply numerator and denominator by y1, y2, y3. What is going to happen to the numerator? Y1, y3 divided by y1 plus y2 plus y3. Okay, and now you see suddenly that both the expressions, this one as well as this one, they are basically the same expression. Okay, sometimes you are operating with y's and sometimes you are operating with z's. So, good news is you do not have to remember two formulae, you have to remember only one. What is the bad news? You still do not know when to use what, right. The two formulae, once it is going to be, it is one formula, once with z, once with y, right. When will you use the z formula and when will you use the y formula? You still do not know what to use when. Okay. So, this is the bad news. All right. Now, the way to look at this is as follows. So, remember when we worked with the T network, right, we used Z parameters and it was very easy to work it out, right. Things were in series straight away, right. Z1, Z2 they were in series, right. So, this T network, there is a lot of seriousness to it. Fine. If I have a word like that, seriousness, right, there is no such word, but let us imagine a word like that, seriousness, right. So, the T network has a lot of seriousness to it and that is why when I wanted an example of Z parameters, I picked up the T network. I told you that I am going to give you easy ones in the class, right. So, in the class all whenever, right, whichever year, right, whichever college, two port networks whenever they are taught, right, first example they will pick up for Z parameters is the T network. Why? Because there is a lot of seriousness in the T network. It is like things are in series. So, in the star, T is star, right, in the star it appears as if things are in series, right, there is some seriousness in the star. The delta on the other hand, it appears that things are in parallel, right. And if you look at it, we used y parameters where conductances add, right. Conductances are adding and that tells you that there is a lot of parallelness in the y parameter in the pi network, right, in the pi or in the delta. Okay. Now, if suppose I have 3 resistors in series 1 ohm, 1 ohm, 1 ohm, how much is it? 3 ohms. I want to make 3 ohms using 3 resistors in parallel. What will I use? 9, 9 and 9. So, 1, 1 and 1 in series is equivalent to 9, 9 and 9 in parallel. Okay. So, if I want a series network to be the same as a parallel network, then the resistance has to be much lesser in the series network. In the parallel network, you will have large resistances. In the series network, you will have small. Fine. So, in the star network, you expect large or small resistors? Small. And in the pi network, you expect large resistors. Okay. In the pi network, you expect small conductances, and in the T network, you expect large conductances. Fine. And how are you going to go from small to large? Or how are you going to go from large to small? You are going to divide by a sum, right. Take the product and divide by a sum, right. That is how you go from something large to something small. Fine. Is it okay? Will you be now able to remember the expression? So, basically what I am saying is that you do not know anything, you only know the form, right. The form is Z1, Z2, some Z times some Z or some Y times Y. So, something times something divided by this is what you, this is the only thing you know. Okay. What happens here? Something large becomes something small. Fine. To go from large to small, this is what you use. Now, suppose you have been given a T network, right. You have been given a T network, you want to go to a pi network. So, T, or you have been given a star network, you want to go to a delta network. Okay. The star network has low resistance, high conductances, and the delta network will therefore need low conductance, because the conductances are going to add in the delta, add up. Fine. So, therefore, we are going to use conductances over here. So, we are going to use y 1 and y 2 of the star and y 1, y 2, y 3 of the star to give me y a or y b or y b, whatever it is, right. Is it fine? So, y a will be y 1, y 2, yeah. You will be able to do it, star delta. We have discussed two parameters, two ways to play with a two port network, right. And how many more ways have we got to do? 4 more ways we have got to learn, right. So, the next would be, instead of V 1 V 2 as independent, I 1 I 2 as dependent, we are going to do mixed. Okay, we are going to mix it up. All right, perfectly okay, perfectly normal. There is nothing wrong here. We are simply going to mix it up. and we are going to say, let us say that I 1 and V 2 are the independent parameters, V 1 and I 2 are the dependent parameters. And what are the units now of the matrix? This is ohms. How about this? No, no dimensions, unitless. This one is also unitless, and this one, last one, Siemens. Fine. And earlier, when everything was resistance, you called it Z, everything was a conductance, you called it Y. Now, you know, it's all mix and match, right, all everything is mixed. So, we call this the set of hybrid parameters. Right, and hybrid is H. So, we are going to call this H 11, H 12, H 21 and H 22. And here you are going to say that look, the other possibility was also hybrid, where I 1 and V 2 were dependent and V 1 and I 2 were independent. This was also hybrid. So, here because we have run out of alphabet, right, after H comes I, and I we can't use. I parameters are a no, right, I is current. Okay, so, we go backwards and we are going to call this the G parameters. Yeah, it is as simple as that. Yeah, right. We are going to use G parameters over here. Right, these are both hybrid parameters, just that you will have to memorize which is which. Okay. The one I have written down is what it is, right. Whenever we say H, I 1 and V 2 are the independent parameters. All right. Off the cuff, it is not so straightforward to memorize, but with a little practice you will realize what is going on. Okay, thank you.